Welcome friends, Igor is here, and in this video we will learn what transformations preserve solution sets of linear systems. In this lesson we will start implementing our strategy for solving linear systems, and we will solve one sample linear system from start to finish. The first step is to understand how we can change the linear system yet preserve its solution set. This can be achieved by so-called elementary equation operations. Given a linear system, the following operations will transform the system into another one, and each of these operations is called an equation operation. Number one is the swap operation. We can swap the locations of any two equations in the list of equations. Number two is the scale operation. We can multiply one equation by a non-zero quantity. Number three is the replacement operation. We can multiply one equation by any quantity and add the result to another equation. Let me illustrate these operations. We have a linear system with three equations in three variables. First, let's swap equations 1 and 3. So we take these two equations and we simply interchange their position in the system. This may look stupid. Why would you want to swap equations in a system? Because it doesn't really change anything. But this operation is useful for our future development of an algorithm that will solve any linear system. Next, let's look at the scale operation. For example, we can take equation number 1 and multiply it by 2. This is the only equation in the system that will change as a result. Finally, let's look at the replacement operation. For example, we can take equation number 1, multiply it by -2, and add the result to equation number 3. Now you see why we've done it this way. By multiplying equation number 1 by -2 and adding the result to equation number 3, we effectively eliminated the variable x1 from equation 3. And this is one of the ideas why we use these operations. The replacement operations allow you to eliminate variables from equations and make your system easier to solve. And now we reached a milestone in this course because we are going to state and prove our first theorem. We're going to prove that the three equation operations preserve solution sets. And that means that if you take a linear system and you apply an equation operation on that linear system, then the transformed system and the original system are equivalent. One of the goals for me in these videos is to show you the thinking process behind constructing proofs. And tip number one is this: before you start proving something, make sure you understand what it is that you're trying to prove. Ask yourself, what is it that I need to prove here? In this case, we need to prove that two linear systems are equivalent. But in order for us to be able to do this, we need to understand what it means for two systems to be equivalent. And this is where the definition of equivalent systems comes in handy. We need to know the vocabulary, because if you don't know what it means for two systems to be equivalent, there is absolutely no way you can prove that two systems are equivalent because you don't know what you're trying to prove. Let's recall that two systems are equivalent if they have the same solution set. So making this translation of the term equivalent systems, we need to prove that two systems have equal solution sets. In other words, in essence, on the general level, we need to prove that two sets are equal. And to prove that two sets are equal, we need to show that the two sets are subsets of each other. Now that we distilled the essence of what exactly we need to prove, let's get to it. Let S denote the solution set of the original linear system, and T denote the solution set of the transformed linear system that we obtained from the original system by applying one equation operation. There are three types of equation operations, so we're going to handle each type at a time. The case of a swap operation is trivial because by changing the position of equations in a system, in no way we affected the solution set of the system. So in this case, it's obvious that a transformed system and the original system have the same solution sets. Now let's look at the scale operation. So we have a generic linear system with m equations and variables, and let's suppose that we take equation number I and we multiply that equation by alpha. Moreover, alpha has to be a non-zero quantity. What you see right now is the original linear system, and this is what a transformed system looks like. Observe, only one equation was changed. Only equation number I now looks different. All other equations in the original and the transformed system are the same. Our goal is to show that the solution set of the original system is a subset of the solution set of the transformed system, and conversely, the solution set of the transformed system is a subset of the solution set of the original system. First, we are going to show that every solution of the original system is also a solution of the transformed system. Now, to be a solution of the transformed system, it has to satisfy every single equation in the transformed system. But we know that all equations in the transformed system are the same as in the original system, except possibly equation number I. Therefore, any solution of the original linear system will satisfy automatically all equations of the transformed system, except possibly equation number I, and therefore our goal is to show that the solution of the original system also satisfies equation number I of the transformed system. Let me take any such solution of the original system. Let's denote it by beta 1, beta 2 through beta n. Our goal now is to show that it satisfies equation number I of the transformed system. Because betas are a solution of the original system, they satisfy all equations of the original system. In particular, betas satisfy the ith equation of the original system. So we know that this equality is a true equality. Let's multiply this equality on both sides by alpha. This is still a true equality, but now this says that betas satisfy equation number I of the transformed system, and therefore betas satisfy all equations of the transformed system, and in particular this argument shows that every solution of the original system is also a solution of the transformed system, and therefore S is a subset of T. Now, let's show the opposite inclusion, that every solution of the transformed system is also a solution of an original system. Again, let's recall that the only difference between the two systems is in equation number I. Therefore, any solution of the transformed system will automatically satisfy all equations of the original system except possibly equation number I. So let me take any solution of the transformed system, beta 1, beta 2 through beta n, and because it is a solution of the entire transformed system, in particular, it satisfies equation number I of the transformed system. But now we are going to use our extra assumption that alpha was a non-zero constant. It is essential in this case, because if alpha is a non-zero number, we can scale this equation by 1 over alpha, which exists because alpha is a non-zero number, and what we see is now betas satisfy equation number I of the original system. Therefore, betas satisfy all equations of the original system, and therefore it is a solution of the original system. This proves that every solution of the transformed system is also a solution of the original system, and it means that T is a subset of S. Now we showed that S is a subset of T and T is a subset of S. Therefore, they are equal as sets, and we have established that if you apply a scale operation to one equation in a linear system, then the new system is equivalent to the original one. Finally, let's look at what happens when we apply a replacement operation. For example, we take equation number I, multiply it by a constant alpha, and add the result to equation number j. So what you see right now is the original linear system, and this is the transformed linear system. Notice that only equation number j has changed. All other equations remain the same. Let's show that S is a subset of T. I'm going to take any solution of the original linear system, beta 1, beta 2 through beta n, and I would like to show that it is also a solution of the transformed system. We know that the two systems have the same equations except equation number j, so this solution automatically satisfies all equations of the transformed system except possibly equation number j. I'm going to substitute betas into the left-hand side of the equation number j of the transformed system. And now I'm going to perform some simple algebraic manipulations. First, I'm going to distribute multiples of beta. So I'm going to combine multiples of betas with the first term in each parenthesis, and then I'm going to combine multiples of beta with the second term in each parenthesis. All terms in the first group are multiples of alpha, so let's factor alpha out. Now look at the first group. What we have inside the parenthesis is the left-hand side of equation number I of the original system. And we know that betas satisfy this equation. Therefore, what we have inside the parenthesis is equal to the right-hand side of equation number I of the original system. Similarly, if you look at the second group, what you have inside the parenthesis is the left-hand side of equation number j of the original system. And because betas are a solution of the original system, they satisfy all equations in that system. In particular, betas satisfy equation number j of the original linear system, and therefore the left-hand side of that equation evaluates to the right-hand side of the equation when you substitute betas for variables. Now look at the beginning and the end of this computation. You will see that this equality says the left-hand side of equation number j of the transformed system is equal to the right-hand side of that equation if you substitute betas for the variables. This shows that betas satisfy equation number j of the transformed linear system, and therefore they are a solution of the transformed system. This shows that S is a subset of T. For the opposite inclusion, I'm going to take any solution of the transformed linear system, and I will show that it is also a solution of the original linear system. Once again, the only difference between the two systems is in equation number j, so this is the one that we need to concentrate on. I'm going to take the left-hand side of equation number j in the original linear system, and I'm going to apply a little trick. I'm going to add 0 to that expression. Of course, by adding 0, I do not change the value of the expression, but I'm going to represent this 0 in a tricky way. I'm going to represent this 0 as alpha bi minus alpha bi. Next, I'm going to replace the first copy of alpha bi with that big term in parentheses. Now, why can I do this? These two expressions are equal because betas satisfy equation number I of the transformed system. And in particular, they also satisfy the scaled equation if you multiply both sides by alpha, as we already proved in the scale operation. Next, I'm going to perform some algebraic manipulations. I'm going to group the terms according to the betas, and this is what we'll have. Now, in each group, we are going to factor out the corresponding copy of beta. But now I can replace the red part with alpha bi plus bj because betas satisfy equation number j of the transformed system. This is exactly the left-hand side of that transformed equation and the right-hand side of the transformed equation. But now you see that this simplifies to simply bj. If you look carefully at the beginning, at the end of this computation, you will see that it shows that betas satisfy equation number j of the original linear system. And therefore, they satisfy all equations of the original system, and so they represent a solution of the original system. This proves that T is a subset of S, and we have proved S is a subset of T, T is a subset of S. Therefore, S and T are equal as sets, and this completes the proof that two linear systems are equivalent. Now we have established that equation operations preserve solution sets. Let's use this knowledge to solve a sample linear system. 3 equations, 3 variables. First, we are going to take equation number 1 multiplied by -1 and add the result to equation number 2. What you see now is the transformed linear system. Please make sure you can repeat this computation. Do you see why I performed this specific operation? What we have achieved is we eliminated the variable x1 from the second equation. Can you guess what comes next? Of course, we're going to take equation number 1, multiply it by -2, and add the result to equation number 3. This way, we have eliminated the variable x1 also from equation 3. Next, I'm going to multiply equation number 2 by -2 and add the result to equation number 3. This eliminates the variable x2 from equation number 3. Next, I'm simply going to scale equation number 3 by -1 to make the coefficient on x3 equal to 1. This linear system can be written more clearly by not writing explicitly the variables which are multiplied by zeros. Now you see that it has this simple, much simpler form than the original system. It looks like a triangle, and these systems are easy to solve, as we will see now. Let's solve this new simple system. Equation number 3 says that x3 must be equal to 4. Then we can substitute this value of x3 into equation number 2, and it tells us that x2 must be equal to -3. Now that we know values of both x2 and x3, we can substitute these values into equation number 1 and find that x1 must be equal to 2. Therefore, this linear system has a unique solution. x1 equals to 2, x2 equals to -3, x3 equals to 4. But this unique solution is also the solution of the original linear system. And the transformed linear system and the original linear system have identical solution sets. Therefore, the original system also has a unique solution, and we know what the solution is. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will introduce the matrix notation for systems of linear equations. I will see you later.